now let's go back to the motivation and think about this a little bit from a technical point of view. And we know that there's an evolution towards the containers. The problem that we have on a computer is that we share it in some fashion while providing near bare metal access to the services is one of our desires. And in many cases we can't achieve this because software systems don't allow us to provide bare metal, such as virtual machines. Virtual machines have for years now provided the full operating system isolation, solving a security problem, but there are limits on performance due to the complex guest operating system that we have to map on to our bare metal infrastructure, including a large memory footprint. So although virtual machines have isolated features, we introduced a lot of overhead. The solution of this is one solution. This is not all of the solutions, but one of the solutions is instead of using virtualization of the entire operating system to only virtualize the application. Instead of duplicating the programs and the libraries, we share them among a group of trusted applications. Introducing the management component allows us to coordinate this, and the introduction of this is actually the containers. And how this technically is being achieved, we try to provide a small highlight to you so that you can initially grasp what the differences are, and then go a little bit deeper into this while focusing on some more technology-related activities. So let us compare between containers, virtual machines, and function as a service. As we can see, a virtual machine, the pros are we have any choice of the operating system. This includes even Windows. Negatives is we have redundancy and resource sharing and overhead from using hypervisors because we have a large-scale memory footprint. So initially, when we are looking at the figure number 1 and look at the first one, this is naturally our standalone application. We have the hardware, we have access to the operating system, we have the runtime library, we have an application. On virtual machines, we are now virtualizing the hardware through a virtual machine, which is its first layer. We have then an operating system on top of this that the virtual machine actually uses, but the runtime and the application layer has access to. But these are separate instantiations of the operating systems. Naturally, this increases the overhead because not only do we have to host the virtual machine, but we also have to host the operating system. On the container side, we have the hardware, the operating system, a small layer of runtime that includes the container staging there. We may want to draw a small line in between to do container management, but we have the runtime and the application separated, and these are our containers. In function as a service, we even integrate the functions into the same runtime environment, and thus we have short-living applications that project functions to the outside world, thus being much more scalable. So this means that if we are looking just at the containers, we have a near native performance in fine-grained resource allocation that we can utilize. We have some security concerns that, however, are going to be resolved with the improvement of the integration of containers into the operating systems. And we have also at this time a problem that some of these containers can be run as root, and you need to have access to the underlying operating system for certain operations. However, when we are looking at the function as a service, these problems disappear because we are only focusing on the function instead of focusing on accessing the runtime library as part of the container. Why do we use virtual containers and not virtual machines? We have already explained in previously a little bit. There is a whole bunch of overhead introduced while using virtual machines. And when we look at virtual machines, the containers offer 3 different key benefits that we need to be looking into. Since they can run on a bare metal infrastructure, containers can be operated more efficiently, and they are closer to bare metal. Because they are smaller resource footprints, the container can enable much higher tenant density on the host. Containerized applications can be managed more effectively with less configuration drift, as it is possible to more easily redeploy services and automate their life cycles. This includes even dynamic migration activities, because the service that has to be migrated is much smaller in contrast to virtual machines. Container adaptation has rapidly expanded with the enterprise IT over the last 2 years. And we have to point out this is a really new trend, and we need to be making sure that you are exposed to this new trend. We can't just look at other older technologies, but we need to be making sure you are on top on the newest level of technologies. Not everything is yet being fully defined, and there's a lot of activities going on, so you can't expect that everything will be working, but this is also research activity, and we as researchers need to be identifying how we can leverage this activity. However, because this is such an important trend within industry, the quality of the software and services that are being developed by it is very, very high. When we look at this, we also have to think about event-driven and serverless computing, which is something that you will be hearing throughout the class, or when you're going outside and searching for resources, where we identify that not only serverless computing is important, that provides a function as a service, so for example Google Cloud Functions, Amazon Lambda Functions, OpenWhisk, OpenLambda, or Azure Functions. And serverless computing was initially very popular in the peer-to-peer community, but we also have to identify that these days we are also moving towards event-driven computing, where we are going out to the edge and integrate events from sensors and from actuators into our environment that we are exposed to. So this means that the cloud owners and cloud providers provide in the future not only cloud-native platforms, but also augment them with short-running and stateless computations in order to support event-driven applications, which scale up and down instantly and automatically. This will change the execution of the unit from maybe minutes for a virtual machine to seconds for functions to milliseconds for serverless functions. And that's a very important trend, and we see that this is all integrated in our architecture, from bare metal to an infrastructure as a service, platform as a service, container orchestrations, and the integration of serverless computing into the same architecture. So what is serverless computing? So let's once more recap this. We have identified that companies will be using this technology at one point, and it's actually not meant to be serverless. It's meant that the function that's being executed can be executed on any arbitrary server, given that there is a description about that this function can be executed on a certain infrastructure. This naturally allows us to completely abstract the hardware out of this and use a platform for deploying such serverless computational functions. So they are currently under the development, and they are not easily a substitute for virtual machines at this time, but they're bringing enough features to the table so that we can start the development and start the discussion about moving away from virtual machines to containers to serverless computing. In 2022, 2/3 of the server workloads will be developed off-premise, and the integration of serverless computing is really important because we can then develop these functions that then can be distributed and executed by others in, for example, a new physical server environment, reducing the overall cost of what needs to be spent into maintaining such large public cloud services. While the number of deployed workloads will more than double in 2022, the definition of on-premises will be challenged by the massive growth of edge computing. This means mobile phones, small-scale computers, your fridge, your washing machine. Now, in order for us to develop a computation and programs for them, wouldn't it be great to have an abstract model that can be executed on all of them, such as through serverless computing, to define what needs to be executed on them? And so people will actually start talking about what's called these days hyperconvergence. And that is a type of infrastructure system with a software-centric architecture that tightly integrates compute and storage, as well as networking and virtualization resources in addition to other technologies into a commodity hardware service or box, which is supported by a single vendor. So this means I can actually put everything in, deliver this. Your fridge has everything in there, and I don't have to look into it. It has all these features included, and they still can connect with other services and with other computers because they integrate tightly with the storage and networking. So IT leaders are currently looking at what really hyperconvergence means, what the potential benefits actually are, and how they can actually leverage this. This is typically done as a hype by all these vendors that you can currently see. They're, simply say this is a hype. But we need to be looking at this from a rational point of view. I believe we will be soon realizing that we have integrated systems that, in contrast to its definition with simplicity, actually puts a heavy burden on the complex IT leaders to make the strategy of developing such devices that integrate this to lead to hyperconvergence. Second, we need to be looking at the following three primary benefits for developers that serverless computing provides. It supports running the code without having to operate the infrastructure, such as servers, storage, and network, because we can focus on the functions. This is really highly appealing to the developers. We can go back to writing programs instead of going back setting up infrastructure. It can enable horizontal scaling due to the autoscaling properties of back-end resources, because we can put many services on the same resource, and if you have many resources, the same services can be potentially outsourced not only on one computer but on multiple. And we have public clouds hosting these infrastructure services, not only on the infrastructure level, but also the serverless frameworks that allow us to instantiate these functions on that infrastructure. So the adaptation of serverless computing is at this time quite nascent. So we will, however, see an increase in this soon happening. So the reason for this is due to the immaturity of the technology, because it requires a rethinking about how do we develop software. However, event-driven workloads will grow really in importance in the next decade, and we will actually see that that's where we will be seeing a lot of growth happening. And that growth is actually catapulted by the existence of containers.